Hello and welcome, fellow travelers, to the Sleepyhead Geographer. Tonight, we're going to deep beneath the surface of our planet's vast oceans, where invisible rivers flow and ancient currents whisper stories of climate and weather that have shaped our world for millions of years. Take a moment to find your most comfortable position, perhaps in your favorite chair by the window or nestled under soft blankets in bed. Let your shoulders relax. Allow your breathing to slow and deepen. If this gentle journey helps you rest, consider a quiet like or subscribe so others can find their way here too. And if you'd like, tell me where you're listening from and what time it is for you. Tonight's journey will take us into the hidden world of ocean currents, those mysterious, powerful flows of water that act as our planet's circulatory system, regulating temperature, distributing heat, and influencing weather patterns from the smallest island to the largest continent. These currents are the unsung heroes of our climate story, working tirelessly and invisibly to maintain the delicate balance that makes life on Earth possible. As we begin our exploration together, let's first take a moment to appreciate the sheer scale of what we're about to discover. Imagine, if you will, that our planet's oceans are not simply vast bodies of water, but rather a complex network of liquid highways that have been operating continuously for millions of years, carrying cargo more precious than any treasure, the very essence of climate stability itself. Picture the Pacific Ocean, so vast that it contains more water than all the other oceans combined, its surface stretching beyond the horizon in every direction. Now imagine that beneath this seemingly calm surface, rivers of water are flowing, some as wide as entire countries, some moving faster than you might walk, carrying temperatures and nutrients from the tropics to the poles and back again. These underwater rivers don't follow the contours of land like the streams and rivers we know on the surface. Instead, they follow the invisible contours of temperature, salinity, and the Earth's own rotation. The Atlantic Ocean, too, plays its part in this grand circulation, hosting some of the most powerful and climate-influencing currents on our planet. The Gulf Stream, which we'll explore in detail during our journey, carries more water than all the world's rivers combined, a warm, swift current that brings tropical heat northward and helps keep Europe's climate surprisingly mild for its northern latitude. In the Indian Ocean, monsoon patterns and seasonal reversals create currents that have guided sailors for thousands of years, while the Arctic and Southern Oceans contribute their own cold, nutrient-rich waters to the global circulation system. Each ocean basin is connected to the others through a web of currents so intricate and interconnected that oceanographers sometimes call it the global conveyor belt, a system that takes roughly 1,000 years to complete one full cycle around the planet. But perhaps most remarkably of all, these ocean currents don't just move water, they move climate itself. They carry heat from the sun-baked equatorial regions toward the poles, and they transport cold water from the ice-covered polar regions back toward the equator. In doing so, they moderate temperatures across the globe, preventing the tropics from becoming unbearably hot and keeping the polar regions from becoming even more frigid than they already are. The story we're about to unfold together is one of connection and consequence, of cause and effect playing out on a global scale over timescales that span from days to millennia. We'll discover how ocean currents influenced the routes that explorers took across uncharted seas, how they affect the weather patterns that bring rain to farmers' fields or storms to coastal cities, and how they're responding to the changing climate of our modern world. We'll explore the science behind these mighty flows, learning about the forces that drive them, from the warming power of the sun to the spinning motion of our planet, from the saltiness of water to the shape of ocean basins carved by millions of years of geological activity. But we'll also uncover the human stories connected to these currents, the tales of sailors who learned to read the ocean's moods, scientists who dedicated their lives to understanding its mysteries, and coastal communities whose entire ways of life are shaped by the waters that flow past their shores. Tonight's journey will be both educational and deeply relaxing, a chance to learn something fascinating about our planet, while also finding the peace and tranquility that comes from contemplating the vast, slow rhythms of the natural world. As we move through our exploration, you might find your mind drifting like a gentle current itself, carrying you toward that peaceful state between waking and sleeping where learning becomes effortless and wonder feels as natural as breathing. Let us begin our journey at the very beginning, dear travelers, in the deep time when our planet's oceans first learned to dance with the forces that would shape them into the climate-regulating system we know today. Close your eyes and imagine traveling back through millions of years, to a time when the Earth was younger and the first ocean currents were being born from the marriage of sunlight, wind, and the planet's own ancient spin. In the beginning, there was the sun, that same warm, life-giving star that bathes us in golden light each morning and sets in brilliant colors each evening. But the sun's gift of energy doesn't fall equally across our planet's curved surface. Picture our Earth as a sphere floating in space, one side always tilted toward our star, receiving the direct, intense heat of those solar rays, while other regions curve away, receiving that same sunlight at increasingly shallow angles until, at the poles, it barely grazes the surface at all. This fundamental inequality, this uneven distribution of solar energy, is where our story truly begins. The sun's rays, striking the equatorial waters with full force, heat the ocean surface to temperatures that can reach into the 80s and 90s Fahrenheit. These warm tropical waters, like a pot of soup gently heating on a stove, become less dense as they warm, causing them to expand and rise. Meanwhile, thousands of miles away, the polar waters receive so little direct sunlight that they remain near freezing, becoming denser and heavier, sinking toward the ocean floor. But our Earth is not a static sphere hanging motionless in space. No, she spins, completing one full rotation every 24 hours, that same rotation that gives us the rhythm of day and night, sunrise and sunset. This spinning motion, which we call the Coriolis effect after the French scientist who first described it, adds a gentle but persistent twist to everything that moves across the planet's surface, including the waters of our oceans. Imagine, if you will, that you're standing at the North Pole, looking down at the Earth as it spins beneath you. From your perspective, the planet rotates counterclockwise, like a record on a turntable. Now picture a drop of water trying to move in a straight line from the equator toward the pole. As it travels northward, the spinning Earth beneath it curves away to the right, causing the water to deflect eastward. In the southern hemisphere, the effect works in reverse, deflecting moving water to the left. This Coriolis effect, combined with the uneven heating from the sun, begins to organize the random motion of ocean waters into the first primitive currents. Warm water, heated by tropical sun and deflected by the planet's rotation, starts to flow in great circular patterns called gyres. These gyres, enormous wheels of moving water, some spanning entire ocean basins, become the foundation upon which all other ocean circulation patterns will build. But there are other forces at work in the birth of ocean currents, forces as fundamental as gravity itself. The moon, our faithful companion, pulls at the waters with her gravitational embrace, creating the tides that surge and retreat along countless coastlines twice each day. These tidal movements, though they might seem separate from the great currents we're exploring, actually help to mix and stir the ocean waters, creating complex interactions between surface and deep waters, between coastal and open ocean environments. The shape of the ocean basins themselves also plays a crucial role in directing the flow of these newborn currents. Picture the Atlantic Ocean, relatively narrow and bounded by the continents of North and South America on one side, Europe and Africa on the other. The currents flowing in this confined space must follow the contours of the continental shelves, deflecting around underwater mountain ranges, squeezing through narrow passages and spreading out into broader areas. These geographical constraints act like the banks of a river, channeling and directing the flow of water in predictable patterns. Now, let's add another layer to our understanding: the role of salinity, the saltiness of seawater, in driving ocean circulation. Not all ocean water contains the same amount of salt. In areas where evaporation is high and rainfall is low, such as the subtropical regions, the sun draws pure water vapor into the atmosphere, leaving behind water with a higher concentration of salt. This saltier water is denser and heavier than fresher water, causing it to sink toward the ocean bottom. Conversely, in regions where rivers discharge massive amounts of fresh water into the sea, or where heavy rainfall or melting ice dilutes the ocean's salinity, the water becomes lighter and tends to float on the surface. The Amazon River, for instance, pours so much fresh water into the Atlantic that a layer of less salty water can be detected hundreds of miles from the river's mouth, creating a distinct interface between the river water and the saltier ocean water beneath. This interplay between temperature and salinity, what oceanographers call thermohaline circulation, creates a three-dimensional movement of water that extends from the surface all the way to the ocean floor. Dense, cold, salty water sinks in polar regions, then spreads along the bottom toward the equator, while warm, lighter water flows along the surface toward the poles to replace it. This creates a vast, overturning circulation, like a slow-motion waterfall that takes centuries to complete one full cycle. As we contemplate these ancient forces that gave birth to ocean circulation, it's worth pausing to appreciate the beautiful simplicity of the physics at work. Heat from the sun, the spin of the earth, the pull of the moon, and the chemistry of salt water. These basic elements, interacting in countless subtle ways, create a system of such complexity and elegance that scientists are still discovering new aspects of how it works. The early ocean currents, formed by these fundamental forces, began to create feedback loops that would influence the Earth's climate for millions of years to come. As warm currents carried tropical heat toward the poles, they moderated the temperature differences between different latitudes. As cold currents brought polar water toward the equator, they created upwelling zones where deep, nutrient-rich water rose to the surface, feeding the first marine ecosystems and eventually influencing the evolution of life itself. These primitive circulation patterns also began to influence atmospheric circulation, the movement of air masses that we experience as weather. Warm ocean currents release heat and moisture into the atmosphere above them, creating areas of low pressure that draw in air from surrounding regions. Cold currents, on the other hand, cool the air above them, creating high-pressure zones and influencing wind patterns. The atmosphere and oceans, we begin to see, are not separate systems, but intimately connected partners in a planetary dance. The birth of ocean currents represents one of the most beautiful examples of how simple physical principles can combine to create systems of astounding complexity and importance. From the fundamental inequality of solar heating to the ancient rhythm of our planet's rotation, from the chemical properties of salt water to the gravitational pull of our moon, these forces conspired to create the circulation system that would become essential to life on Earth as we know it. As we prepare to delve deeper into the specific mechanisms and patterns of ocean circulation, take a moment to appreciate this cosmic choreography, the way our planet, our star, and our moon work together to keep the waters of our world in constant, purposeful motion. These same currents that first began to flow in the ancient seas continue today, carrying not just water but the very conditions that make our modern climate possible. Now, dear fellow travelers, let us journey deeper into one of the most remarkable and important circulation systems on our planet. A vast, slow-moving river of water that flows not along the surface where we might see it, but through the deepest parts of our oceans, connecting every ocean basin in a single, all-continuous loop that takes roughly 1,000 years to complete one full cycle. Oceanographers call this the thermohaline circulation, from the Greek words thermo, meaning heat, and haline, meaning salt. But many prefer the more poetic name, the Great Global Conveyor Belt. Tonight, as we explore this hidden circulatory system of our planet, imagine yourself floating peacefully in these deep, ancient waters, carried along by currents so vast and powerful that they transport more water than all the world's rivers combined, yet so gentle that their movement is barely perceptible to human senses. To truly understand the Great Conveyor Belt, we must first visit the places where this remarkable journey begins. The cold, wind-swept waters of the North Atlantic and the ice-covered seas around Antarctica. Picture, if you will, the waters near Greenland and Norway, where winter temperatures plunge well below freezing and fierce winds whip across the ocean's surface. Here, something magical happens that sets the entire global circulation system in motion. The surface waters in these regions become extraordinarily cold, sometimes just above freezing, and as they cool, they become denser, heavier than the warmer waters beneath them. But temperature alone is not the only factor at work. In these polar regions, when sea ice forms, it traps only the pure water molecules, leaving behind the salt. This process, called brine rejection, makes the remaining liquid water even saltier and thus even denser. Dense, cold, salty waters become so heavy that they begin to sink, like invisible waterfalls cascading downward through the ocean depths. In the North Atlantic, this sinking occurs in several key locations: in the Labrador Sea between Greenland and Canada, in the waters between Greenland and Scotland, and in the Norwegian Sea. Scientists have given this cold, dense water mass a name: North Atlantic Deep Water, or NADW for short. As this cold water sinks, it doesn't simply disappear into the abyss. Instead, it begins to flow southward along the ocean floor, following the contours of underwater mountain ranges and deep ocean basins. Picture this deep current as a river of cold water, sometimes several miles wide and thousands of feet thick, flowing silently through the deepest parts of the Atlantic Ocean at depths of 2 to 3 miles below the surface. Meanwhile, in the Southern Ocean around Antarctica, a similar but even more dramatic process is taking place. Here, the circumpolar current, the only current that flows completely around the globe, uninterrupted by any landmass, creates some of the most turbulent and mixing-intensive waters on the planet. The combination of extremely cold temperatures, strong winds, and the formation of Antarctic sea ice creates the densest water masses in the world's oceans. These Antarctic waters, even colder and denser than their North Atlantic counterparts, sink to the very bottom of the ocean basins and flow northward into all 3 major oceans: the Atlantic, Pacific, and Indian. This Antarctic bottom water, as scientists call it, represents the deepest layer of the global circulation system, creeping along the ocean floor at speeds so slow that it takes centuries for these waters to travel from Antarctica to the equator. But what goes down must eventually come up, and this is where the Great Conveyor Belt reveals its truly global nature. As the cold, deep waters flow toward the equator in all 3 major ocean basins, they gradually warm up through contact with the warmer waters above them and through the geothermal heat that seeps up from the Earth's interior through underwater volcanic vents and hot springs scattered across the ocean floor. In the Pacific and Indian Oceans, these deep waters eventually rise to the surface through a process called upwelling, bringing with them nutrients that have accumulated during their long journey through the deep ocean. This upwelling occurs gradually over vast areas, but it's most pronounced in certain regions where winds and ocean topography create the right conditions for deep water to rise toward the surface. The return journey of these waters to the North Atlantic is just as remarkable as their initial sinking. Picture warm surface currents flowing like rivers of liquid sunshine across thousands of miles of ocean. In the Pacific, the warm water flows westward across the equatorial regions, then northward along the coasts of Asia, carrying tropical heat toward the Arctic. In the Indian Ocean, the warm return flow is influenced by the seasonal monsoons, creating currents that reverse direction twice each year. But it's in the Atlantic Ocean that the return flow is most dramatic and most important to global climate. Here, warm surface waters flow northward in several major current systems, the Gulf Stream along the eastern coast of North America being the most famous, carrying tropical heat and moisture far into the northern latitudes. This warm return flow completes the circuit, eventually reaching those same cold polar regions where the entire cycle began, ready to cool down, become dense, and sink once again to begin another 1,000-year journey around the globe. The scale and importance of this great conveyor belt are almost beyond human comprehension. The amount of water it transports is staggering. Estimates suggest that about 15 million cubic meters of water flow through this system every second. To put that in perspective, that's enough water to fill a space the size of a football field to a height of 150 feet every single second, continuously, year after year, century after century. This circulation system acts as our planet's climate thermostat, distributing heat from the tropical regions where it's abundant to the polar regions where it's scarce. Without this heat transport, computer models suggest that Europe would be 10 to 15 degrees Fahrenheit colder on average, cold enough to make countries like Britain and France as frigid as northern Canada. The thermohaline circulation literally makes certain regions of our planet habitable. But the Great Conveyor Belt is not a simple, unchanging system. Like a living organism, it responds to changes in its environment, speeding up or slowing down based on temperature, salinity, and wind patterns. During ice ages, when large amounts of the planet's water were locked up in continental ice sheets, the circulation was much stronger because the remaining ocean water was saltier and denser. During warmer periods, increased rainfall and melting ice can dilute the polar waters, making them less dense and slowing down the circulation. Scientists have discovered evidence that this circulation system has actually shut down completely several times in Earth's history, causing dramatic and rapid climate changes. When the conveyor belt stops, the heat transport from equator to poles is severely reduced, leading to a phenomenon known as the bipolar seesaw. The northern hemisphere cools rapidly, while the southern hemisphere warms, creating entirely different weather patterns across the globe. One of the most fascinating aspects of the thermohaline circulation is how it connects events happening in completely different parts of the planet. Changes in rainfall patterns over the Sahara Desert can affect the salinity of the North Atlantic. Melting ice in Greenland can influence upwelling patterns in the Pacific. The growth or retreat of Antarctic ice sheets can modify current patterns that affect monsoons in Asia. The Great Conveyor Belt reveals our planet as a single, interconnected system, where cause and effect can be separated by thousands of miles and hundreds of years. Modern oceanographers study this system using an array of sophisticated tools: satellite measurements of sea surface temperature and height, robotic floats that drift with the currents and report their positions and measurements via satellite, and deep ocean moorings that monitor temperature and salinity changes over many years. These observations have revealed that the Great Conveyor Belt is not uniform or steady, but pulses and varies like a slow heartbeat, responding to seasonal changes, weather patterns, and longer-term climate cycles. As we prepare to explore other aspects of ocean circulation, take a moment to appreciate the profound beauty and importance of this global system. The water molecules that might be flowing past the coast of Greenland today may have begun their journey from the warm tropical Pacific decades ago, carrying with them the chemical signatures of their long voyage and the climate history of our planet. In the Great Conveyor Belt, we see one of nature's most elegant solutions to the problem of distributing energy around a spherical planet, a solution that has operated continuously for millions of years and will continue long after we're gone. As we drift gently from the depths of the Great Conveyor Belt back toward the sun-warmed surface of our planet's oceans, let us now turn our attention to a completely different but equally fascinating aspect of ocean circulation: the swift, wind-driven currents that flow along the ocean's surface like rivers of liquid light, carrying warmth, marine life, and human history across the vast expanses of our blue planet. Unlike the deep thermohaline circulation we've just explored, which moves at the stately pace of centuries and millennia, surface currents dance to a much quicker rhythm, responding to the daily breath of our planet. The winds that blow across the ocean's surface, transferring energy from the moving air to the water below. These surface currents, though they extend only a few hundred meters down from the ocean's top, carry enormous amounts of heat and have profound impacts on global weather patterns, marine ecosystems, and human civilization. Picture yourself lying peacefully on your back, floating on warm, calm waters somewhere in the middle of the Pacific Ocean. Above you, trade winds blow steadily from the northeast, their constant pressure creating gentle ripples on the water's surface. But these winds are doing much more than simply creating waves. They're actually dragging the surface water along with them, like invisible hands pulling a silk scarf across a table. This is how surface currents are born, through the friction between moving air and water, a process so fundamental that it connects the rhythm of atmospheric circulation directly to the flow of ocean waters. To understand surface currents, we must first understand the great wind systems that drive them. Imagine our planet as seen from space, with bands of air circulation wrapping around it like ribbons on a gift. Near the equator, intense solar heating creates a belt of rising air that scientists call the Intertropical Convergence Zone, or ITCZ. This rising air creates a zone of generally light winds. The doldrums, where sailing ships of centuries past would sometimes find themselves becalmed for days or weeks. As this warm, moist air rises high into the atmosphere, it spreads outward toward both poles, eventually cooling and sinking back toward the Earth's surface, around 30 degrees north and south latitude. This creates the subtropical high-pressure zones, regions of generally calm weather and clear skies, but also the birthplace of some of the most consistent and important wind patterns on our planet. From these subtropical highs, surface winds flow in two directions. Some air flows back toward the equator, creating the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The Coriolis effect. That subtle but persistent influence of our planet's rotation deflects these winds, creating the steady, reliable trade winds that once carried European explorers westward across the Atlantic and Pacific Oceans. Other air flows poleward from these subtropical highs, becoming the westerly winds of the middle latitudes, the same winds that brought early American settlers across the continent and that today carry weather systems from west to east across North America and Europe. These westerlies are less steady than the trade winds, varying with the seasons and the passage of storms, but they too play a crucial role in driving surface ocean currents. Now, let us see how these great wind systems create the surface current patterns that girdle our planet. In each major ocean basin, the combination of trade winds, westerlies, and the constraining influence of continental coastlines creates large circular current systems called gyres. Picture these gyres as enormous whirlpools, but whirlpools that take years rather than minutes to complete one full rotation, and that span thousands of miles rather than feet. In the North Atlantic, the trade winds push surface water westward across the tropical Atlantic, where it piles up against the eastern coast of the Americas and is deflected northward, forming the beginning of the Gulf Stream. The westerlies then carry this warm water eastward across the North Atlantic toward Europe, where it becomes the North Atlantic Drift. Finally, cold winds from the Arctic push this water southward along the coasts of Spain and North Africa as the Canary Current, completing the circle. The Pacific Ocean, being much larger than the Atlantic, hosts even more dramatic gyre systems. The North Pacific gyre follows a similar pattern to the North Atlantic, with the warm Kuroshio Current flowing northward along the coasts of Japan and the Philippines, then eastward across the North Pacific as the North Pacific Current, and finally southward along the western coast of North America as the California Current. But it's in the South Pacific that we find perhaps the most extensive gyre system on Earth. Here, the trade winds drive the South Equatorial Current westward across thousands of miles of open ocean, carrying warm water from the eastern Pacific near Peru all the way to the coasts of Australia and New Guinea. This current is so broad and powerful that it actually splits into multiple branches as it approaches the western Pacific, sending warm water both northward and southward around the various island chains and continental margins. These surface current systems are not static, unchanging rivers in the sea. Instead, they pulse and shift with the seasons, responding to changes in wind patterns, solar heating, and the complex interactions between ocean and atmosphere. The monsoon regions of the Indian Ocean provide perhaps the most dramatic example of seasonal current reversal, where the direction of surface flow actually changes completely twice each year. During the Northern Hemisphere summer, intense heating of the Asian landmass creates low pressure zones that draw moist air inland from the ocean, creating the southwest monsoon winds. These winds drive surface currents northeastward across the Indian Ocean, bringing warm water and abundant rainfall to the coasts of India and Southeast Asia. But during the winter, the pattern reverses completely. The Asian landmass becomes a high-pressure zone, and the northeast monsoon winds drive surface currents in the opposite direction, creating entirely different patterns of ocean circulation and weather. One of the most fascinating aspects of surface currents is how they interact with underwater topography to create unique oceanographic phenomena. When swift surface currents encounter underwater mountain ranges, seamounts, or continental shelves, they can create upwelling zones where deep, nutrient-rich water is forced to the surface. These upwelling areas become biological hotspots, supporting some of the most productive marine ecosystems on Earth. The California Current system provides an excellent example of this process. As this cold current flows southward along the western coast of North America, persistent winds push the surface water offshore through a process called Ekman transport. The Coriolis effect causes water moving under the influence of wind to deflect slightly to the right in the northern hemisphere, so winds blowing along the coast actually push surface water away from the shore. This creates a void that must be filled by water rising from below, cold, nutrient-rich water that supports the incredibly productive marine ecosystems of the California coast. Where different surface currents meet, they create some of the most dynamic and biologically important regions of the ocean. These current boundaries, or fronts, are zones of intense mixing where waters of different temperatures, salinities, and nutrient contents come together. The Gulf Stream front, where the warm waters of the Gulf Stream meet the colder waters of the Labrador Current, creates an underwater boundary so sharp that it can sometimes be seen from space in satellite images. These frontal zones are highways for marine life, concentrating nutrients and providing feeding grounds for everything from tiny plankton to great whales. Many marine species time their migrations to coincide with the seasonal movements of these fronts, following them across thousands of miles of ocean. Bluefin tuna, for example, use the warm edges of the Gulf Stream as a superhighway for their annual migrations between feeding and spawning grounds. Surface currents have shaped human history in ways both subtle and profound. The trade winds and their associated currents provided the highways that connected the Old and New Worlds, carrying Columbus westward to the Americas and the Spanish treasure galleons back to Europe. The prevailing westerlies helped speed the great clipper ships on their races around Cape Horn, while the doldrums could trap sailing vessels for weeks in the middle of the ocean. Even today, modern cargo ships plan their routes to take advantage of favorable currents and avoid opposing ones, saving fuel and time on ocean crossings that still take weeks to complete. Commercial fishing fleets use detailed knowledge of current patterns to locate the upwelling zones and frontal areas where fish are most likely to concentrate. And increasingly, oceanographers and climate scientists monitor these surface currents as indicators of larger changes in the Earth's climate system. As we prepare to dive deeper into specific current systems in our continuing journey, take a moment to appreciate the elegant simplicity and profound complexity of surface ocean circulation. Born from the marriage of wind and water, shaped by the rotation of our planet and the geography of ocean basins, these currents create a dynamic, ever-changing tapestry of movement that connects every part of our planet's surface waters. In their swift flows and seasonal rhythms, we see the ocean's immediate response to atmospheric changes, a reminder that our planet's climate system operates through countless interconnected feedbacks and relationships. Among all the ocean currents that flow around our planet, none is more famous, more studied, or more important to human civilization than the mighty Gulf Stream, that swift river of warm water that flows northward along the eastern coast of North America, carrying tropical heat toward the Arctic and fundamentally shaping the climate of both North America and Europe. Tonight, let us follow this remarkable current on its journey, from its birth in the warm waters of the Caribbean to its transformation into the North Atlantic drift that bathes the shores of Western Europe. Picture yourself floating in the crystal-clear, turquoise waters of the Caribbean Sea, where the water temperature hovers around 80 degrees Fahrenheit year-round and the trade winds blow steadily from the east. Here, in this tropical paradise, the Gulf Stream begins its life not as a single current, but as a complex system of flows that will eventually merge into one of the most powerful currents on Earth. The Caribbean waters, heated by intense tropical sunshine and pushed westward by the trade winds, begin to pile up against the coastlines of Central America and the Yucatan Peninsula of Mexico. This warm water has nowhere to go but northward, squeezing through the narrow channel between Cuba and Mexico's Yucatan Peninsula in what oceanographers call the Yucatan Current. Already, at this early stage, the current is carrying an enormous volume of water, roughly 30 million cubic meters per second, which is about 600 times the flow of the Amazon River. As this warm current enters the Gulf of Mexico, it begins to take on the characteristics that will make it so famous. The Gulf of Mexico acts like a giant bathtub, where the incoming warm water circulates in a clockwise pattern, heated even further by the intense subtropical sun and by the shallow sun-warmed waters over the continental shelf. The water becomes not just warm, but stratified, with the warmest, lightest water floating on top of slightly cooler, denser layers below. This stratification is crucial to the Gulf Stream's character. The warm surface layer acts like a blanket, trapping heat and creating a current that flows swiftly along the surface while barely affecting the deeper waters below. As the current loops around the Gulf of Mexico, it gathers momentum and volume, picking up additional warm water from the surrounding seas and preparing for the next phase of its remarkable journey. The true Gulf Stream is born when this warm water finds its escape route from the Gulf of Mexico through the Florida Straits, the narrow channel between the Florida Keys and Cuba that is less than 100 miles wide and only about 3,000 feet deep at its shallowest point. Here, constrained by the shallow water and narrow passage, the current accelerates dramatically, like water shooting through the nozzle of a garden hose. Emerging from the Florida Straits, the Gulf Stream becomes a clearly defined river of warm water, flowing northward along the continental shelf edge at speeds that can reach 5 miles per hour, fast enough that a person could almost keep pace by walking briskly along the shore. The current is typically about 50 miles wide and extends down about 3,000 feet below the surface, but its core of fastest-moving water is much narrower and shallower, creating a distinct boundary between the warm Gulf Stream water and the cooler coastal and offshore waters that surround it. The volume of water that the Gulf Stream carries is almost beyond comprehension. At its peak, near Cape Hatteras in North Carolina, the current transports roughly 150 million cubic meters of water per second. That's more than 3,000 times the combined flow of all the rivers on Earth. To put this in perspective, imagine every river, stream, and creek on every continent suddenly flowing together in a single channel. Then multiply that flow by 3,000. That's the Gulf Stream at its most powerful. But the Gulf Stream carries more than just water. It carries heat, enormous amounts of it. The current transports roughly 1.4 petawatts of heat energy northward, which is equivalent to about 100 times the total energy consumption of all human civilization. This heat transport is what makes the Gulf Stream so climatically important, effectively acting as a massive heating system that warms the entire North Atlantic region. As the Gulf Stream flows northward along the coast of the southeastern United States, it follows the edge of the continental shelf with remarkable precision, like a river following its banks. The current's western boundary is sharply defined by the temperature and color difference between the warm, deep blue Gulf Stream water and the cooler, often greenish coastal water. This boundary is so distinct that it can be seen from space in satellite images, appearing as a sharp line dividing two different shades of blue. The eastern edge of the Gulf Stream is equally fascinating but more complex. Here, the warm current water gradually mixes with the cooler waters of the Sargasso Sea, creating a series of eddies, meanders, and rings that constantly form, drift away from the main current, and eventually dissipate. These Gulf Stream rings, some of them hundreds of miles across, carry warm or cool water far from the main current, creating pockets of tropical conditions in otherwise temperate waters, or bringing cool, nutrient-rich water into warm tropical regions. One of the most remarkable aspects of the Gulf Stream is its variability and dynamic behavior. While the current maintains its general northward flow year-round, it constantly shifts position, speeds up and slows down, and develops meanders that can extend hundreds of miles east and west of its average position. These meanders are not random. They follow predictable patterns related to underwater topography, seasonal heating and cooling, and the complex interactions between the Gulf Stream and other current systems. During winter months, the Gulf Stream typically flows closer to shore and moves more swiftly as the temperature contrast between the warm current and the cooling continental waters becomes more pronounced. In summer, the current often shifts farther offshore and slows down slightly, as the coastal waters warm up and reduce the temperature gradient that helps drive the current's flow. The Gulf Stream is not just a current of warm water, it's a biological highway, one of the most important migration routes in the Atlantic Ocean. The warm, nutrient-poor waters of the central Gulf Stream might seem like a biological desert, but the edges of the current, where it meets cooler waters, are incredibly productive zones where marine life concentrates in remarkable abundance. Many species of fish, sea turtles, marine mammals, and seabirds use the Gulf Stream as a migration corridor, taking advantage of the current's swift flow to travel long distances with minimal energy expenditure. Loggerhead sea turtles, for example, spend their juvenile years riding the Gulf Stream and associated currents in a great circular journey that takes them from nesting beaches in Florida and the Carolinas, north with the Gulf Stream, then east across the Atlantic with the North Atlantic Current, and eventually back to their home waters after a journey that can take a decade to complete. The boundaries where the Gulf Stream meets other water masses create upwelling zones and frontal systems that concentrate nutrients and support remarkable concentrations of marine life. These areas are feeding grounds for everything from tiny copepods to great whales, and they support some of the most important commercial fisheries in the North Atlantic. As the Gulf Stream flows northward along the coast, it gradually begins to change character. Near Cape Hatteras, North Carolina, the current encounters the southward-flowing Labrador Current, creating one of the most dynamic and biologically productive regions in the North Atlantic. Here, the warm Gulf Stream water meets the cold, fresh water from the Arctic, creating intense mixing and upwelling that supports abundant marine life, but also creates some of the most treacherous maritime conditions in the world. This collision of currents has earned Cape Hatteras the nickname Graveyard of the Atlantic, due to the hundreds of ships that have been lost in these turbulent waters over the centuries. The meeting of warm and cold air masses above these contrasting water temperatures creates frequent fog, sudden storms, and rapidly changing weather conditions that have challenged mariners for as long as humans have sailed these waters. Beyond Cape Hatteras, the Gulf Stream begins its transformation from a coastal current into an open ocean flow. The current separates from the continental shelf and flows northeastward into the deep Atlantic, gradually broadening and slowing as it moves into deeper waters. This is where the Gulf Stream begins to become the North Atlantic Current, though the transition is gradual and the exact boundary between the two is somewhat arbitrary. As the current moves into the open Atlantic, it begins to interact with other water masses and current systems in increasingly complex ways. The warm water continues to release heat to the atmosphere, moderating temperatures across the North Atlantic and helping to maintain the relatively mild climate of Western Europe. Computer models suggest that without this heat transport, countries like Britain, Ireland, and Norway would have climates similar to those of Labrador and Alaska, cold enough to dramatically change the ecosystems and make agriculture much more challenging. The Gulf Stream's influence extends far beyond the waters it directly touches. The heat and moisture it releases into the atmosphere affect weather patterns across the entire North Atlantic region, influencing the tracks of storms, the patterns of rainfall, and the timing of seasonal changes. The current's strength and position can affect the formation and movement of hurricanes in the Atlantic, as these powerful storms draw energy from warm ocean waters. Climate scientists have discovered that the Gulf Stream's strength and position vary not just seasonally, but also over much longer timescales, responding to changes in global climate patterns. During the last ice age, when much of North America and Northern Europe were covered by massive ice sheets, the Gulf Stream was much weaker and followed a different path, contributing to the much colder conditions that prevailed across the North Atlantic region. Today, oceanographers monitor the Gulf Stream constantly using satellites, underwater instruments, and research vessels, as changes in the current can provide early warning of larger changes in the global climate system. The Gulf Stream serves as a kind of canary in the coal mine for climate change, as alterations in its strength, temperature, or path can signal broader shifts in ocean circulation patterns that might affect weather and climate around the world. As we prepare to explore other remarkable current systems, take a moment to appreciate the Gulf Stream's unique combination of power, beauty, and importance. This single current system, born in the tropical Caribbean, nurtured in the Gulf of Mexico, and matured in the open Atlantic, demonstrates how local conditions can have global consequences, and how the movement of ocean water connects weather patterns, ecosystems, and human societies across thousands of miles and multiple continents. In the Gulf Stream, we see the ocean at its most dynamic and influential, a reminder of the profound ways that moving water shapes our world. As we drift away from the swift surface currents and the mighty Gulf Stream, let us now descend into one of the ocean's most mysterious and life-giving phenomena: the ancient process of upwelling, where deep, cold waters rise from the abyss to the surface, bringing with them nutrients accumulated over centuries and supporting some of the most productive ecosystems on our planet. Tonight, we'll explore these vertical highways in the sea, where the boundary between surface and deep ocean dissolves, and where some of Earth's most remarkable biological treasures are sustained by waters that last saw sunlight decades or even centuries ago. Picture yourself floating in the surprisingly cold waters off the coast of Peru, where the Humboldt Current flows northward along the western edge of South America. The water here is much colder than you might expect for a location so close to the equator, often 15 to 20 degrees Fahrenheit cooler than waters at similar latitudes on the other side of the Pacific. This coolness is not an accident, but rather the signature of one of the most powerful upwelling systems on Earth, where deep ocean waters rise to the surface in a process so productive that it supports some of the largest fisheries in the world. The mechanism behind upwelling is both elegant and complex, driven by the same Coriolis effect that influences all moving objects on our spinning planet. Along the western coasts of continents in both hemispheres, persistent winds blow parallel to the shoreline. In the northern hemisphere, these winds typically blow from north to south, while in the southern hemisphere, they blow from south to north. But here's where the magic happens. The Coriolis effect causes the surface water, when pushed by these alongshore winds, to deflect away from the coast. Imagine standing on a beach facing the ocean, with the wind blowing from your right toward your left, parallel to the shoreline. The Coriolis effect causes the wind-driven surface water to move not directly with the wind, but at an angle away from the shore. In this case, directly away from where you're standing. As this surface water moves offshore, it creates a void near the coast that must be filled by water from below. Nature abhors a vacuum, even in the ocean, so deep water rises to replace the surface water that has been pushed away from the shore. This rising water, this upwelling, brings with it characteristics that have been shaped by its long journey through the deep ocean. The upwelled water is cold, often 40 to 50 degrees Fahrenheit colder than the surface waters it replaces. It's also incredibly rich in nutrients, nitrates, phosphates, silicates, and trace elements that are essential for marine life, but that are typically scarce in surface waters because they've been consumed by organisms and have sunk toward the ocean floor when those organisms die. To understand why upwelled water is so nutrient-rich, we must think about the ocean's great recycling system. In the sunlit surface waters, microscopic plants called phytoplankton use these nutrients, along with carbon dioxide and sunlight, to grow and reproduce through photosynthesis. These tiny plants form the base of the ocean's food web, feeding small animals called zooplankton, which in turn feed fish, which feed larger fish, and so on up the food chain. But when these organisms die, they sink toward the ocean floor like a slow-motion snowfall, carrying with them all the nutrients they incorporated during their lives. Most of this organic matter is decomposed by bacteria, during its long descent through the water column, releasing the nutrients back into the surrounding water. But this decomposition happens far below the surface, in the cold, dark depths where there are no plants to use these recycled nutrients. Over time, this process concentrates nutrients in the deep ocean while depleting them in the surface waters. The deep water becomes like a vast storehouse of fertilizer, accumulating nutrients for decades or centuries, until upwelling brings them back to the surface where they can once again fuel the growth of marine life. The most famous and productive upwelling systems occur along the eastern boundaries of the major ocean basins, the coasts of California, Peru, northwest and southwest Africa, and parts of Australia. Each of these systems has its own characteristics and seasonal patterns, but all share the same basic mechanism and the same remarkable productivity. Off the coast of California, the upwelling season typically begins in spring when the North Pacific high-pressure system strengthens and shifts northward, creating northwesterly winds that blow parallel to the coast. These winds drive the California current southward and push surface water offshore, allowing cold, nutrient-rich water to rise from depths of 150 to 300 feet. The upwelled water creates a band of cold, productive ocean extending 10 to 50 miles offshore, supporting everything from microscopic diatoms to blue whales. But perhaps nowhere is upwelling more dramatic or more important to human society than along the coast of Peru, where the Humboldt Current creates one of the most productive marine ecosystems on Earth. Here, the upwelling is so intense and consistent that it supports massive populations of anchovies. The Peruvian upwelling system is unique in several ways. The Andes Mountains, rising directly from the coast, create offshore winds that enhance the upwelling process. The Peru-Chile Trench, one of the deepest parts of the Pacific Ocean, runs parallel to the coast, allowing very deep, very nutrient-rich water to rise relatively close to shore. And the system operates year-round, unlike many upwelling regions that have distinct seasonal cycles. This constant upwelling creates water so rich in nutrients that it can support an almost unimaginable abundance of life. During peak periods, the waters off Peru can contain more fish biomass per unit area than anywhere else in the world's oceans. The anchovy populations alone can number in the billions, creating a food source so abundant that it supports not only vast numbers of seabirds, but also marine mammals, larger fish, and one of the world's most important commercial fisheries. The biological productivity of upwelling zones extends far beyond the fish and marine life that live directly in these waters. Many species use upwelling areas as critical feeding grounds during migrations, timing their journeys to coincide with the periods of maximum productivity. Gray whales, for example, feed almost exclusively in the upwelling zones of the North Pacific, building up fat reserves during the summer that sustain them through their long migration to breeding grounds in Mexico. Seabirds from across the Pacific converge on upwelling zones during their breeding seasons, with some species flying thousands of miles to reach these productive waters. The timing of upwelling can determine the success or failure of entire breeding seasons for these birds, as the abundance of small fish determines whether parent birds can successfully feed their chicks. Not all upwelling occurs along coastlines. In the tropical Pacific, a different type of upwelling occurs along the equator itself, driven by the complex interaction between trade winds and the Coriolis effect. Here, the trade winds blowing from east to west cause surface water to diverge away from the equator northward in the northern hemisphere and southward in the southern hemisphere. This creates a zone of upwelling that extends for thousands of miles along the equator, bringing cold, nutrient-rich water to the surface in the middle of the tropical Pacific. This equatorial upwelling system is less intense than the coastal upwelling zones, but it covers a much larger area and plays a crucial role in global ocean circulation and climate. The cold water that rises along the equator helps to moderate sea surface temperatures in the tropical Pacific, influencing weather patterns across the entire Pacific basin and beyond. Upwelling systems are intimately connected to global climate patterns, both influencing and responding to changes in atmospheric circulation. During El Niño events, for example, the normal upwelling along the coast of Peru weakens dramatically as warm water from the western Pacific spreads eastward, suppressing the rise of cold, nutrient-rich water. This has catastrophic effects on marine ecosystems and fisheries, but it also influences weather patterns around the world. The strength and location of upwelling systems can also provide clues about long-term climate changes. As global temperatures rise and weather patterns shift, scientists are monitoring upwelling zones for signs of how these critical ecosystems might respond to a changing climate. Some models suggest that upwelling might intensify in some regions as temperature gradients between land and sea increase, while other areas might see weakened upwelling as wind patterns shift. The water that rises in upwelling zones carries with it not just nutrients, but also a record of its journey through the deep ocean. Scientists can analyze the chemical signatures of upwelled water to trace its origins. Some water might have last been at the surface in the North Atlantic decades ago, while other water might carry the signature of Antarctic waters that sank to the deep ocean centuries ago. These deep waters that fuel upwelling systems are like libraries, storing information about past climate conditions in their temperature, salinity, and chemical composition. When they finally return to the surface, they bring news from the deep ocean, telling us about conditions that existed long before any human instruments were there to measure them. As we prepare to explore other aspects of ocean circulation, take a moment to appreciate the profound importance of upwelling systems to life on Earth. These vertical connections between the surface and the depths represent one of the ocean's most elegant recycling systems, ensuring that nutrients accumulated in the deep ocean eventually return to fuel new life at the surface. In upwelling zones, we see the ocean at its most generous, supporting an abundance of life that seems almost miraculous in its richness and diversity. The ancient waters that rise in these systems have traveled vast distances and stored nutrients for decades or centuries, making their return to the sunlit surface a kind of resurrection, a renewal of the potential for life that connects the deep, mysterious abyss with the vibrant, productive surface waters where most marine life thrives. Now, dear travelers, let us turn our attention to one of the most fascinating and influential phenomena in the world's oceans, a periodic disruption of normal circulation patterns that demonstrates just how interconnected our planet's climate system truly is. Tonight, we'll explore El Niño and its counterpart, La Niña, along with other climate oscillations that reveal the ocean's profound influence on weather patterns around the globe, affecting everything from rainfall in Peru to monsoons in Asia, from hurricane seasons in the Atlantic to droughts in Australia. Picture yourself floating in the warm waters of the tropical Pacific during a typical year, somewhere near the international date line, where the ocean stretches endlessly in all directions. The water here is remarkably warm, often 85 degrees Fahrenheit or higher, heated by intense tropical sunshine and accumulated in this western part of the Pacific by the steady push of the trade winds. This pool of warm water, larger than the entire North American continent, is one of the most important features of our planet's climate system, and its behavior influences weather patterns across half the globe. Under normal conditions, this warm water stays put in the western Pacific, held there by the trade winds that blow steadily from east to west along the equator. Meanwhile, on the eastern side of the Pacific, along the coasts of Peru and Ecuador, cold water wells up from the depths, creating the productive upwelling system we explored in our previous journey together. This normal state, warm water in the west, cold upwelling in the east and steady trade winds in between creates predictable weather patterns that have persisted for thousands of years. But every few years, something remarkable and disruptive happens to this stable system. The trade winds, for reasons that scientists are still working to fully understand, begin to weaken or even reverse direction. When this happens, that massive pool of warm water in the western Pacific begins to slosh eastward like water in a bathtub, spreading across the tropical Pacific and eventually reaching the coasts of Peru and Ecuador, where it suppresses the normal upwelling of cold, nutrient-rich water. This phenomenon was first noticed by Peruvian fishermen, who observed that every few years around Christmas time, the normally cold coastal waters would become unusually warm, the abundant fish populations would disappear, and heavy rains would fall in regions that were normally dry. Because of its timing near Christmas, they called this phenomenon El Niño, Spanish for the little boy or the Christ child. During an El Niño event, the entire tropical Pacific undergoes a dramatic transformation. The warm water spreading eastward carries with it not just heat, but also the potential for intense evaporation and heavy rainfall. Areas that normally receive little precipitation, such as the deserts of coastal Peru and southern California, can experience devastating floods, while regions that depend on regular rainfall, such as parts of Australia and Southeast Asia, may suffer severe droughts. The mechanism behind these far-reaching effects lies in the intimate connection between ocean temperatures and atmospheric circulation. Warm ocean water acts like a giant heating pad, warming the air above it and causing it to rise. This rising air creates areas of low pressure that draw in moisture-laden air from surrounding regions, often resulting in heavy rainfall and thunderstorms. Conversely, when ocean temperatures are cooler than normal, the air above tends to sink, creating high-pressure zones that suppress cloud formation and rainfall. But El Niño's influence extends far beyond the Pacific Ocean. The changes in atmospheric circulation patterns that it triggers can affect weather systems around the entire globe through a phenomenon called teleconnections, long-distance connections between weather patterns in different parts of the world. During El Niño events, the jet stream, that high-altitude river of air that guides weather systems across North America, often shifts southward, bringing unusually mild winters to the northern United States and increased storminess to the southern states. In the Atlantic Ocean, El Niño typically suppresses hurricane activity by creating wind shear. Differences in wind speed and direction at different altitudes that tear apart developing tropical storms before they can become fully formed hurricanes. Meanwhile, in the Indian Ocean, El Niño can disrupt the monsoon patterns that billions of people depend on for agriculture and water supply. El Niño has a counterpart, an opposite phase called La Niña, the little girl, that occurs when the normal patterns of the tropical Pacific become even more extreme than usual. During La Niña events, the trade winds strengthen, pushing even more warm water toward the western Pacific and enhancing the upwelling of cold water along the South American coast. The temperature contrast between the eastern and western Pacific becomes more pronounced than normal, creating its own set of global weather impacts. La Niña events tend to bring cooler than normal temperatures to the tropical Pacific, but they can intensify weather patterns in other parts of the world. La Niña often contributes to more active hurricane seasons in the Atlantic, as the reduced wind shear allows tropical storms to develop more easily. In North America, La Niña typically brings colder, snowier winters to the north and drier conditions to the south. In Australia, La Niña often enhances the normal rainfall patterns, sometimes contributing to flooding in eastern parts of the continent. The alternation between El Niño and La Niña conditions, along with the neutral periods in between, creates what scientists call the El Niño Southern Oscillation, or ENSO for short. This oscillation typically completes one full cycle from one El Niño through La Niña and back to the next El Niño, over a period of 2 to 7 years, though the timing is irregular and difficult to predict with precision. Each El Niño and La Niña event is unique, varying in strength, duration, and specific impacts. Some El Niño events are relatively weak and brief, causing only minor disruptions to normal weather patterns. Others, like the El Niño events of 1982 to 1983 and 1997 to 1998, are so strong that they cause billions of dollars in damage worldwide and affect the lives of hundreds of millions of people. The 1997 to 1998 El Niño, often called the El Niño of the century, demonstrated just how powerful these events can be. Sea surface temperatures in the eastern tropical Pacific rose more than 9 degrees Fahrenheit above normal, causing massive disruptions to marine ecosystems and triggering extreme weather events around the globe. Indonesia and Australia suffered severe droughts and wildfires, while Peru and Ecuador experienced devastating floods. Even far from the Pacific, the effects were felt. East Africa experienced unusually heavy rains, while parts of Asia suffered through severe droughts. Understanding and predicting ENSO events has become one of the most important goals of climate science, as advance warning can help societies prepare for the weather changes these events bring. Scientists now monitor the tropical Pacific constantly using an array of instruments: satellite measurements of sea surface temperature, networks of buoys that measure temperature and currents throughout the water column, and sophisticated computer models that attempt to forecast how the system will evolve. The challenge of ENSO prediction lies partly in the complex feedback loops between the ocean and atmosphere. Small changes in sea surface temperature can trigger atmospheric responses that either amplify or dampen the initial change, making the system highly sensitive to initial conditions. This sensitivity means that while scientists can often predict the onset of El Niño or La Niña events several months in advance, forecasting their ultimate strength and duration remains challenging. ENSO is not the only climate oscillation that affects global weather patterns. In the North Atlantic, a phenomenon called the North Atlantic Oscillation, or NAO, influences winter weather across Europe and eastern North America. The NAO is based on the strength and position of the semi-permanent high and low pressure systems that dominate North Atlantic weather patterns. When these pressure systems are particularly strong and well positioned, they can create persistent weather patterns that last for weeks or months. During positive NAO phases, strong pressure gradients across the North Atlantic create powerful westerly winds that bring mild, wet winters to northern Europe and cold, snowy conditions to eastern North America. During negative NNAO phases, these pressure gradients weaken, allowing Arctic air to penetrate further south into Europe, while bringing milder conditions to eastern North America. In the Pacific Ocean, scientists have identified an even longer-term oscillation called the Pacific Decadal Oscillation, or PDO, which operates on timescales of 20 to 30 years rather than the few years typical of ENSO. The PDO involves changes in sea surface temperature patterns across the entire North Pacific, with alternating phases of warming and cooling that can persist for decades. The PDO appears to modulate the effects of ENSO, making El Niño events stronger or weaker depending on the phase of the longer-term oscillation. During positive PDO phases, the North Pacific tends to be warmer than normal along the coasts of North America and cooler in the Central Pacific, while negative PDO phases reverse this pattern. These long-term changes affect everything from salmon populations in Alaska to winter temperatures across North America. What makes these climate oscillations so fascinating is how they demonstrate the interconnected nature of Earth's climate system. Changes in ocean temperatures in one part of the world can influence rainfall patterns thousands of miles away, while atmospheric pressure changes over one ocean basin can affect storm tracks over completely different continents. These teleconnections remind us that our planet operates as a single, integrated system where everything is connected to everything else. The study of climate oscillations has also revealed how human activities are beginning to interact with these natural cycles. As global temperatures rise due to increasing greenhouse gas concentrations, scientists are working to understand how phenomena like ENSO might change in a warmer world. Some models suggest that El Niño events might become more frequent or more intense, while others predict changes in their geographical patterns or seasonal timing. As we prepare to explore the final aspects of how ocean currents shape our climate, take a moment to appreciate the profound influence these oscillations have on daily life around the world. From the rice paddies of Indonesia to the ski slopes of Colorado, from the hurricane tracks in the Atlantic to the drought patterns in Australia, these periodic changes in ocean circulation affect billions of people in ways both subtle and dramatic. In ENSO and other climate oscillations, we see the ocean at its most influential, demonstrating its power to reorganize global weather patterns and remind us that the boundaries between ocean and atmosphere, between local and global, between present and future, are far more fluid than we might imagine. These oscillations are the ocean's way of breathing, of changing its rhythm, and in doing so, changing the rhythm of weather and climate across our entire planet. As we near the end of our oceanic journey together, let us explore one of the most profound and immediate ways that ocean currents touch our daily lives. Through their influence on the weather patterns that determine whether we need an umbrella when we step outside, whether farmers' crops will receive enough rain to grow, and whether coastal communities need to prepare for hurricanes or enjoy calm, sunny days. Tonight, we'll discover how the movement of water thousands of miles away can determine the weather outside your window, and how the ancient circulation patterns we've explored together weave themselves into the fabric of atmospheric circulation to create the complex, ever-changing tapestry of global weather. Picture yourself standing on a beach at dawn, watching the sun rise over waters that stretch endlessly toward the horizon. The gentle breeze on your face, the temperature of the air, the humidity you feel, and the clouds forming overhead are all influenced by the temperature of the ocean water before you. Water that may have traveled thousands of miles through various current systems before arriving at this shore. The ocean beneath that sunrise is not just a passive backdrop to the weather. It is an active participant, constantly exchanging heat, moisture, and energy with the atmosphere above. The relationship between ocean currents and weather patterns is one of continuous give and take, a conversation between water and air that has been ongoing for millions of years. Warm ocean currents release enormous amounts of heat and moisture into the atmosphere, creating the conditions for cloud formation, rainfall, and the development of storm systems. Cold currents, on the other hand, cool the air above them, creating high-pressure zones and generally suppressing precipitation, while often generating fog when warm, moist air passes over their cooler waters. To understand how ocean currents influence weather, we must first appreciate the ocean's role as our planet's great heat reservoir. Water has a remarkable ability to store heat, much greater than air or land, which means that the oceans can absorb vast amounts of solar energy during warm periods and release it slowly over time. This thermal inertia of water is what gives coastal areas their characteristically moderate climates, with cooler summers and warmer winters compared to interior regions at the same latitude. When warm ocean currents like the Gulf Stream carry tropical heat toward higher latitudes, they don't just transport warm water, they transport the potential for warm weather. As these currents flow northward, they continuously release heat to the atmosphere through evaporation and direct heat transfer. The water that evaporates carries enormous amounts of latent heat. The energy required to change liquid water into water vapor, which is released when that water vapor eventually condenses to form clouds and precipitation. The influence of the Gulf Stream on European weather provides one of the clearest examples of how ocean currents shape regional climate patterns. Without the heat transported by this remarkable current system, computer models suggest that Britain would have a climate similar to that of Labrador in Canada, with average temperatures 15 to 20 degrees Fahrenheit colder than they actually are. The warmth carried by the Gulf Stream and its extension, the North Atlantic Drift, is what allows palm trees to grow in southwestern Ireland and makes possible the relatively mild winters that characterize much of Western Europe. But the Gulf Stream's influence on weather extends far beyond simply warming the air. The heat and moisture it provides fuel the development of the low-pressure systems that track across the North Atlantic, bringing the changeable weather patterns that are characteristic of European climate. These storm systems, energized by the temperature contrast between warm ocean currents and cold continental air masses, create the prevailing westerly winds that dominate weather patterns across Europe and eastern North America. The seasonal variations in ocean current strength and position create corresponding changes in weather patterns that we experience as the changing seasons. During winter in the Northern Hemisphere, the Gulf Stream typically flows stronger and closer to shore, as the temperature contrast between the warm current and the cooling continental air masses becomes more pronounced. This enhanced current flow provides more heat to the atmosphere, helping to moderate winter temperatures along the eastern coast of North America and supporting the development of the storm systems that bring winter precipitation to much of the continent. In summer, as continental air masses warm and the temperature contrast between land and sea decreases, the Gulf Stream often shifts farther offshore and its influence on coastal weather diminishes. This seasonal migration of warm currents is mirrored by similar patterns in other ocean basins, creating predictable seasonal changes in regional weather patterns around the world. Perhaps nowhere is the connection between ocean currents and weather more dramatic than in the formation and behavior of tropical weather systems. The hurricanes, typhoons, and cyclones that represent some of the most powerful weather phenomena on Earth. These massive storm systems draw their energy almost entirely from warm ocean waters, and their strength, path, and duration are intimately connected to the temperature and circulation patterns of the currents beneath them. Hurricanes form only over waters that are at least 80 degrees Fahrenheit, and they strengthen rapidly when they encounter even warmer waters or areas where warm currents have pooled heat near the surface. The loop current in the Gulf of Mexico, an extension of the Gulf Stream system, creates a reservoir of extremely warm water that can rapidly intensify hurricanes that pass over it. Hurricane Katrina in 2005 and Hurricane Michael in 2018 both underwent rapid intensification when they encountered these exceptionally warm waters. The path that hurricanes take as they move across the ocean is also influenced by current patterns, though in more subtle ways than their initial formation and intensification. Ocean currents can affect the atmospheric pressure patterns and upper-level wind flows that steer these massive storm systems, while the heat and moisture released by warm currents can influence the development of the high and low pressure systems that guide hurricane tracks. The interaction between hurricanes and ocean currents is not one way. These powerful storms also affect the currents themselves. The intense winds and waves generated by hurricanes mix the upper layers of the ocean, bringing cooler water from below to the surface and spreading the warm surface water over a larger area. This mixing can temporarily weaken warm currents and create cooler sea surface temperatures that persist for weeks after a hurricane has passed, influencing the behavior of subsequent storms in the same region. In the Indian Ocean and Western Pacific, the relationship between currents and weather creates one of the most important and predictable weather patterns on Earth. The monsoon systems that bring life-giving rainfall to billions of people across Asia, Africa, and Australia. The monsoons are fundamentally driven by the seasonal heating and cooling of large land masses, but ocean currents play a crucial role in supplying the moisture and energy that make these massive rainfall systems possible. During the Northern Hemisphere summer, intense heating of the Asian continent creates low-pressure zones that draw moist air inland from the surrounding oceans. The warm waters of the Indian Ocean, heated by intense tropical sunshine and circulated by seasonal current reversals, provide an enormous source of moisture for this process. As the southwest monsoon winds blow across these warm waters, they pick up vast amounts of water vapor that will eventually fall as rainfall across India, Southeast Asia, and parts of East Africa. The timing and strength of monsoon rainfall are intimately connected to sea surface temperatures and current patterns in the Indian Ocean. When ocean temperatures are warmer than normal, the monsoons tend to be stronger, bringing abundant rainfall but also the risk of flooding. When ocean temperatures are cooler, monsoon rainfall may be reduced, potentially leading to drought conditions across regions that depend on these seasonal rains for agriculture and water supply. Along many coastlines around the world, the interaction between warm air and cold ocean currents creates one of the most characteristic and locally important weather phenomena: marine fog. This thick, often persistent fog forms when warm, moist air moves over the cold waters of upwelling currents or cold boundary currents, causing the water vapor in the air to condense into countless tiny droplets suspended in the atmosphere. The fog that regularly shrouds the coast of California, from San Francisco Bay to the Mexican border, is a classic example of this process. As the warm, dry air of the continental interior moves westward toward the coast, it encounters the cold waters of the California Current and the upwelling zones along the continental shelf. The rapid cooling causes the moisture in the air to condense, creating thick fog banks that can extend miles inland and persist for days at a time. This marine fog is not just a local weather curiosity. It plays a crucial role in the ecology and water cycle of coastal regions. In areas like the Pacific Northwest and coastal California, fog provides a significant source of moisture for forests and other vegetation, particularly during the dry summer months when rainfall is scarce. The fog drip from trees in coastal forests can contribute as much moisture as several inches of rainfall per year. The influence of ocean currents on regional weather patterns extends to precipitation patterns across entire continents. The warm waters transported by currents provide the moisture source for many of the world's major river systems, while the atmospheric circulation patterns driven by current-related temperature gradients determine where that moisture will fall as rain or snow. In North America, the moisture that feeds the great river systems of the continent, the Mississippi, the Colorado, the Columbia, originates largely from evaporation over warm ocean currents in the Gulf of Mexico, the Atlantic, and the Pacific. The Gulf Stream provides moisture that eventually falls as rain across the eastern United States, while the warm currents of the Pacific supply water vapor that becomes snow in the Rocky Mountains and rain in the Pacific Northwest. The seasonal strength and position of these currents help determine whether the western United States experiences wet or dry years, whether the Great Plains receive enough spring rainfall for successful crops, and whether the Northeast faces mild or severe winters. These connections between distant ocean areas and continental weather patterns demonstrate how truly interconnected our planet's climate system is. Ocean currents also play a crucial role in the development of extreme weather events that can affect millions of people and cause billions of dollars in damage. Heat waves, for example, often develop when persistent high-pressure systems become established over regions where warm ocean currents have heated the lower atmosphere. These high-pressure systems can stall weather patterns, causing hot, dry conditions to persist for weeks or months. The European heatwave of 2003, which caused tens of thousands of deaths and widespread ecological damage, was partly related to sea surface temperature patterns in the Atlantic that influenced the position and strength of atmospheric pressure systems. Similarly, the Russian heat wave of 2010 was connected to sea surface temperature, anomalies that affected the jet stream patterns over Eurasia. Cold spells and severe winter weather can also be influenced by ocean current patterns. When warm currents weaken or shift position, they can allow cold air masses to penetrate much farther toward the equator than usual. The polar vortex events that have brought extremely cold weather to North America in recent years are partly related to changes in the temperature gradients between different ocean regions, which affect the strength and position of the jet stream. The relationship between ocean currents and weather patterns operates not just on daily and seasonal timescales, but also over much longer periods that we experience as climate change. As global temperatures rise and ice sheets melt, the patterns of ocean circulation that have remained relatively stable for thousands of years are beginning to shift, with potentially profound implications for regional weather patterns around the world. Changes in the strength or path of major current systems like the Gulf Stream could dramatically alter precipitation patterns across Europe and North America. A weakening of the thermohaline circulation could reduce heat transport to northern regions, potentially cooling some areas even as global temperatures rise. These changes would not happen overnight, but over decades or centuries, gradually shifting the climate patterns that human societies have adapted to over thousands of years. Scientists are working to understand these long-term connections between ocean circulation and climate, using everything from paleoclimate records preserved in ocean sediments to sophisticated computer models that simulate the behavior of the coupled ocean-atmosphere system. This research is crucial for understanding how our planet's climate might continue to change in the future and how human societies might need to adapt to new patterns of temperature, precipitation, and extreme weather events. As we contemplate these vast scales of interaction between ocean and atmosphere, it's worth remembering that these same processes that shape global climate patterns also influence the weather we experience every single day. The morning fog that might greet you when you step outside, the afternoon thunderstorm that develops on a summer day, the winter storm that brings snow to your region, all of these are connected to the movement of ocean currents thousands of miles away and the complex interactions between water and air that we've been exploring together. In the relationship between ocean currents and weather patterns, we see one of the most immediate and practical ways that the ocean touches human life. These connections remind us that we are all, quite literally, connected to the sea. Not just through the water cycle that brings rain to our fields and snow to our mountains, but through the vast circulation systems that regulate the temperature and humidity of the air we breathe and influence the storms that shape our seasons. As we prepare for the final part of our journey together, take a moment to appreciate how the gentle movement of water in distant seas becomes the wind outside your window, how the ancient circulation patterns we've explored become the weather forecast you check each morning, and how the health of ocean currents thousands of miles away might determine whether your garden receives enough rain to flourish in the coming growing season. And so, dear fellow travelers, we find ourselves at the end of our oceanic journey, having followed the hidden rivers of the sea from their birth in the marriage of sunlight and planetary motion, through their roles as the great circulatory system of our planet, to their intimate connections with the weather patterns that touch our daily lives. As we prepare to return to our peaceful evening rest, let us take a few quiet moments to reflect on the profound beauty and importance of the ocean currents that continue to flow, even now, in their ancient patterns beneath the starlight. Throughout our time together tonight, we have discovered that the ocean is far from the static, unchanging body of water it might appear to be from the shore. Instead, it is a dynamic, living system, constantly moving, constantly changing, constantly connecting distant parts of our planet through the circulation of water that carries heat, nutrients, and life itself across thousands of miles, and through depths measured in miles rather than feet. We have seen how the simple inequality of solar heating, combined with the ancient spin of our Earth, creates circulation patterns of breathtaking complexity and global importance. From the great conveyor belt that takes 1,000 years to complete one journey around our planet, to the swift surface currents that respond to seasonal changes in wind patterns, these movements of water represent one of nature's most elegant solutions to the challenge of distributing energy and resources across a spherical world. On the Gulf Stream, we encountered one of the ocean's most powerful and influential currents, a river of warm water that flows with the force of thousands of terrestrial rivers combined, carrying tropical heat northward and fundamentally shaping the climate of two continents. This single current system demonstrates how local conditions, the heating of Caribbean waters, the shape of ocean basins, the direction of prevailing winds, can have consequences that reach across oceans and influence the lives of millions of people. In the upwelling zones, we discovered the ocean's great recycling system, where ancient waters rise from the depths carrying nutrients accumulated over decades or centuries, creating some of the most productive ecosystems on our planet. These vertical highways in the sea remind us that the boundary between surface and depth, between past and present, is far more fluid than we might imagine, and that the ocean operates on timescales that dwarf human experience while still influencing our daily lives. Through our exploration of El Niño and other climate oscillations, we have seen how the ocean breathes with rhythms measured in years and decades, how changes in one part of the Pacific can influence rainfall patterns around the globe, and how the intimate connections between ocean and atmosphere create a single integrated climate system where everything is connected to everything else. These oscillations remind us that our planet operates as a unified whole, where cause and effect can be separated by vast distances and long periods of time. And in our final exploration of how ocean currents shape weather patterns, we discovered the most immediate and practical ways that these ancient circulation systems touch human life. The warmth or coolness of the air outside your window, the timing of seasonal rains, the development of storms and the paths they take. All of these are influenced by the temperature and movement of waters that may be thousands of miles away, connecting your local weather to the global ocean in ways both subtle and profound. Perhaps the most important lesson from our journey together is the profound interconnectedness of our planet's systems. Ocean currents do not operate in isolation, but as part of a complex web of relationships that connect every part of our world. The carbon dioxide absorbed by phytoplankton in upwelling zones affects atmospheric chemistry around the globe. The heat transported by warm currents influences not just regional temperatures, but also atmospheric circulation patterns that affect weather on distant continents. The nutrients brought to the surface by deep water upwelling support marine ecosystems that are connected to terrestrial food webs through migrating seabirds and marine mammals. These connections extend through time as well as space. The water molecules flowing in today's Gulf Stream may have last been at the surface during the age of sailing ships, carrying with them the chemical signatures of past climate conditions. The deep waters rising in upwelling zones today were last exposed to the atmosphere when our grandparents were young, bringing nutrients accumulated over decades back to fuel new life at the surface. The circulation patterns we observe today are responses to geographical changes that occurred millions of years ago, while also being influenced by human activities that began just a few centuries ago. In the study of ocean currents, we encounter one of nature's most beautiful examples of how simple physical principles can combine to create systems of astounding complexity and importance. The basic forces that drive these currents, the heating power of the sun, the rotation of our planet, the chemical properties of salt water, the pull of gravitational forces, are the same forces that have operated since the oceans first formed billions of years ago. Yet their interactions create circulation patterns so complex that we are still discovering new aspects of how they work. This complexity emerges from simplicity, order from apparent chaos, and global consequences from local conditions, all hallmarks of what scientists call emergent properties, where the behavior of the whole system is greater than and different from the sum of its parts. Ocean circulation represents one of the most magnificent examples of this principle in the natural world, demonstrating how the interaction of simple physical laws can create systems capable of regulating an entire planet's climate. As we reflect on our journey through these oceanic realms, it's worth remembering that humans have always been connected to ocean currents long before we understood the scientific principles that drive them. Polynesian navigators used their knowledge of currents and swells to find tiny islands across thousands of miles of open Pacific. European explorers rode the trade winds and their associated currents to reach the New World. Fishermen around the world have learned to read the subtle signs that indicate where currents bring nutrients to the surface and concentrate marine life. Today, our connection to ocean currents is more direct and immediate than ever before. Satellite communications rely on understanding how atmospheric conditions influenced by ocean temperatures affect signal transmission. Global supply chains depend on shipping routes planned to take advantage of favorable currents. Climate predictions that influence agricultural planning, water resource management, and disaster preparedness all depend on our understanding of how ocean circulation patterns are changing and might change in the future. Our enhanced understanding of ocean currents also brings with it a profound responsibility. As we have seen throughout our journey, these circulation systems are not immune to change. They have varied naturally throughout Earth's history, and they are beginning to respond to human influences on the global climate system. The warming of ocean waters, the melting of polar ice, and changes in atmospheric circulation patterns all have the potential to alter the current systems that have remained relatively stable throughout human history. The health of ocean currents is intimately connected to the health of our entire climate system. Changes in these circulation patterns could affect everything from regional weather patterns to global food production, from the distribution of marine life to the frequency of extreme weather events. Understanding these connections and working to minimize harmful human impacts on ocean circulation represents one of the great challenges and responsibilities of our time. As we conclude our peaceful journey together, take a moment to appreciate the quiet majesty of the processes we have explored. Even now, as you settle into rest, the great currents of the world's oceans continue their ancient flows. The Gulf Stream carrying warmth northward through the Atlantic darkness, deep waters rising in upwelling zones to begin their return to the sunlit surface, the great conveyor belt maintaining its slow but steady circulation around the globe. These currents flow without fanfare or recognition, operating on scales of time and space that can dwarf human perception, yet intimately connected to the weather outside your window, the climate that shapes your region, and the long-term habitability of our planet. In their steady, purposeful movement, we see one of nature's most elegant and essential systems. A reminder that we live on a dynamic, living planet where everything is connected to everything else through invisible threads of cause and effect, action and consequence. Let the rhythm of these ancient currents carry you gently towards sleep, dear travelers, knowing that you are part of a planet whose systems work in harmony to maintain the conditions that make life possible. In the movement of ocean waters around our world, we see not just fascinating science, but also profound beauty. The beauty of a system that has operated for millions of years and will continue long after we are gone, connecting past and future, near and far, surface and depth in an eternal dance of water and climate that shapes our world. Rest now and good night.